Hello class. In this lesson today, we are going to once again look at separation of variables as a method of solution for first order differential equations. But today we're going to focus on finding a particular solution to the problem, which means that after we solve the differential equation, we'll also be able to solve for the constant of integration. So here is problem 34 from exercise 31.2. We have ds by dt is the secant of s. Further, we're given this. T is 0 when s is 0. So this is the extra information we're given so that we can go ahead and solve for the constant. Okay, so let's begin by manipulating this equation. You can see that the differential dt cannot remain in that denominator. So the first thing we're going to do is multiply both sides of the equation by dt. Having done that, now we look at this term and see that the differential is dt, but here we have the variable s. So that cannot be, so now we better divide both sides of the equation by secant s. And we end up with this ds over the secant of s is dt. And this is the point at which, now that the variables are separated correctly, we would think about integration. And we're not going to have any trouble integrating the number 1 with respect to t. But how will we integrate 1 over secant s? Well, in fact, we don't have to. We know that 1 over secant s is equal to the cosine of s. So that's one of our basic trig identities. So we can change the left side to cosine of s ds. And now we're going to integrate both sides of the equation. Okay, so what is the integral of cosine s? So you can look it up here. The integral of cosine s will be sine s. So left side will be sine s. What's the integral of the number 1 with respect to t? That's t. And here, of course, is where we would introduce one constant of integration for the whole equation. This right here is called the general solution. But we would like to find a particular solution, and that means solving for c. And how can we solve for c? Well, we can substitute s and t that were given. So let's suggest that we substitute these values like this. T is 0 when s is 0. So I'm going to put a 0 here and a 0 here. And that will give me the sine of 0 is 0 plus c. Now, you may know that the sine of 0 is 0. And if you didn't know that, you can just use your calculator to evaluate that. So we end up with 0 is 0 plus c. So what does that mean? It means that the value of c is 0. So we can go back to the general solution, which is here, substituting 0 right there, and we'll get this. The sine of s is t plus 0, or in other words, the sine of s is t. And this is the particular solution we desire. Okay, so This kind of question is solved very much like those in the previous two lessons, except that once we have the general solution, we go a little bit further. We use the given values in order to determine that constant. Okay, so I'd like to do another one with you now. That was 34. Now this question is 36. It says x dy is y ln x dx. So we're going to start with that. And as you know, the thing that we must do is beside the differential dy, we should not have x. And beside the differential dx, we should not have y. So I can start maybe by dividing both sides of the equation by x. And that would look like this. And now I'm going to divide both sides of the equation by y and ln y. And in doing so, we get this. dy over y ln y is dx over x. Variables are separated properly, so it is time to integrate. Okay, the right side of the equation can be integrated in this way. The integral of dx over x is just the ln of x. And of course, we would have a constant of integration. And you can find that here, of course. The integral of du over u is ln u. Okay, the absolute value signs are implied even if I don't write them on the paper. Okay, so we end up with ln x plus c. Now, for this integral here, I'm going to go to the bottom of the page. So we have dy over y ln y. So we're going to use a u substitution to work this out. So there are only really a couple of possibilities. U can be y, but that wouldn't work because its derivative is just 1, so there's no way ln y would be involved. So the really only other option is to allow u to be the ln of y. If u is the ln of y, then du is the derivative of the ln of y, and the derivative of the ln of y is 1 over y. So we end up with 1 over y times dy. Okay, so u is the ln of y. So right here we'd be putting a u. Okay, so the u is in the denominator. And dy over y is exactly what this is equal to. 1 over y times dy is the same as dy over y. So the dy over y part is the du. So we have du over u. So this integral becomes exactly the integral of du over u. Right? If we took du, which is this, and then we divided it by this, it would look exactly like this. Okay, so now what is the integral of du over u? Well, that's just the ln of u. But of course we wouldn't leave it with a u in it. Here we would replace u with ln y. All right, so the strange integral here on the left side is the natural logarithm of ln y. So the left side is the ln of y. Okay, so that's kind of a tricky one there, but again, u is here. This is what we called u, and this dy over y is exactly du. So this is how the integral is determined. Okay, so this right here, this is the general solution. And now, if we hope to find a particular solution, we must use this information given. So when x is 2, y is e. So this means we can substitute 2 right here and e right there. So we're going to have the ln of e is equal to the ln of 2 plus c. And from this, we can work out the value of c. Now I'm just going to go grab a calculator. Just give me one moment. Okay, so, oops, I think I'm in, what's that called? Number systems mode there. Okay. So you may know that the ln of e is 1, but if you didn't know that, I just want to show you how you could work that out, right? So you want the ln of e, but you have to put a 1 here as the exponent. So this is how you would evaluate the ln of e. And you can see that that is equal to 1. So we end up with the inside here equal to 1. Like that. And so now this left side is now the ln of 1. And again, you might know that that's 0. But if you didn't, you could punch that in also. The ln of 1 is 0. Okay, so we have 0 on the left side. The ln of e is 0. And on the right side, we have ln 2 plus c. And so that means the value of c is 0 minus ln 2. So that's our value of c. So how do we form a particular solution? We go back to the general solution, and right where c is, we substitute negative ln 2. So the left side is the ln of y, and on the right we have ln x minus ln 2. And that is a particular solution. However, we are able to change the look of that a little bit. For example, we can combine these two logarithms. If we have subtraction here, they combine here in a quotient. So the left side stays the same, the right side is the ln of x over 2. And now, given that this is an equation and both sides are natural logarithms, this means we can equate the arguments. So ln of y is x divided by 2, like that. Or further, x is 2 ln y. All right, but I'll just leave it like that. I'm pretty much out of room, and this is a beautiful way to write the final answer anyway. Okay, so in problem 36, we come up with the general solution after effectively separating the variables and integrating both sides. Substitute the given values to come up with one form of the particular solution. Combine the logarithms on the right, and that allows you to equate the arguments here. All right, so that is a second example, and I will do one more with you. So the last problem I'd like to do with you today is problem 38. We have 2y cos y dy minus the sine of y dy is y sine y dx. So 1, 2, 3 terms. Hopefully you can identify which term is the main problem here. Right in this term, because the differential is dx, we cannot have the variable y here. So how can we fix this? By dividing all terms by y sine y. So let's do that. All right, so we have this right now. That's dividing all 3 terms by y sine y. And now let's simplify these terms here. So first thing, of course, is that the y's here will cancel. And we'll have 2 cos y over sine y. And here, sine y can cancel. Okay, so we could write 2 cos y over sine y dy here, and then it would require a u substitution in order to integrate, or we can simplify cosine y over sine y using an identity. Here, cosine y over sine y is the cotangent of y. So this term becomes 2 cotangent y dy. The next term is just 1 over y dy or dy over y. And here just dx. And now everything's set. We are going to integrate. So I'm just going to write that down, that our next job is to integrate. And what we have to do, of course, is integrate each term. So here, 2 will be multiplied by the integral of cotangent y. And luckily, you can find that here as well. The integral of cotangent y is the ln of the sine of y. So again, if I don't put the absolute value signs in, it's implied anyway. So it's the ln of the sine of y. The integral of dy over y, of course, is the ln of y. You know that. We've used that many, many times, but it's here. And what is the integral of dx? Well, that's the integral of 1 dx, and it's x. And here we need our constant. Okay, so this is what we have as our, we could call this the general solution. Okay, so this is the general solution. All right, I think it's easier to not simplify this until we've gone ahead to solve for that c value. And how will we do that? This question gives us this information. X is 0 when y is pi over 2. So let's use that now. Okay, so I'm going to be substituting pi over 2 here as well as here, and a 0 right there. Okay, so I substituted x is 0 and y is pi over 2. All right, so this is sine of y here, or sine of pi over 2, more specifically, is the argument of the logarithm. So we should work this value out first, okay? So you might know that the sine of pi over 2 is 1, but if you didn't, you could work that out. However, you do need to be in radians. Okay, make sure you're in radians. And then you could do the sine of pi over 2, for example. Okay, so that's 1. So then we want to work out what 2 times the ln of 1 is. Well, the ln of 1 is 0, okay? Here you go, ln of 1 is 0. So this is 2 times 0. So this whole term becomes a 0. And then we have minus the ln of pi over 2 is equal to c. And so the value of c is the ln of pi over 2. Now that's not a nice number, right? The ln of pi over 2 is a complete mess. So I wouldn't want to use that in my solution, okay? So I'm gonna keep it in this form and just put it right here. So we go back to this general solution now, but where c is, we actually have negative ln of pi over 2. So I'm going to write this line out. So we have x minus the ln of pi over 2. And that is a particular solution for this problem. However, we could simplify this considerably. So one thing we could do is actually collect all of the logarithms together. So unlike the last question, there is one term that is not a logarithm. So what I'm going to do to solve this one, or to tidy this one up, I'm just going to collect all the logarithms. So I'm going to, in other words, bring this logarithm to the left side where we will be adding. So it'll be plus the ln of pi over 2, just like that. And now I'd like to combine these logarithms, but you might remember that we can't do that with this coefficient here. The coefficient becomes the exponent on the argument. So this becomes the sine of y squared. Hopefully you remember that property of logarithms. Okay, so the coefficient here can become the exponent here. And now we can put these together. How are they combined? Well, in the numerator we would have pi over 2 and the sine of y all squared. In the denominator we would have y. Like that. Okay, and that's because remember when there is subtraction, you end up with a quotient. So the terms preceded by negative signs end up in the denominator, and those terms preceded by positive signs end up here in the numerator. Okay, and we could write, I mean, that's perfect to me. I like that just fine. You could write it a little differently as well. For example, the 2 here could drop to the denominator, so 2y would be down here, and up top is pi, and the sine of y all squared, or the sine squared of y. Okay, so that's just another possibility. And as I said, the absolute value signs, I don't always include them, but there we go. All right, so that would be a beautiful final answer for number 38. Okay, so I'd like to suggest that you do go ahead and practice. I have selected 3 problems from your textbook for you to try, and you can see that referenced in Blackboard. Okay, thanks a lot. Have a great day.